Okay, so this morning Davide will tell you about fundamentals of light microscopy. Just to introduce you, Davide Accardi graduated from the University of Palermo in Marine EnvironmentalSciences in 2005. Then he finished his PhD in 2012 at the Max Planck Institute in Germany. So he studied self-organization and dynamics of intracellular molecules. So after the PhD, he joined the microscopy facility at Max Planck, where he specialized in imaging and image analysis. And so during this experience, he contributed, as he was saying, for the development of the light sheet microscopy technology, which was recognized as method of the year by the journal Nature Methodin. So since 2017, Davide is the scientific and managing leader of the Bioimaging facility at the Champalimaud Foundation, where he monitors and helps a lot of projects related with neuroscience and cancer research. So welcome, Davide. We are very happy to have you here. And the floor is yours, till one.
Thank you, Nancy.
With a coffee break in the middle.
Thank you for the fantastic introduction. Okay. I'm the head of the ABBE platform at Champalimaud, as Carolina was saying, and I will tell you about, so I will make an introduction of the basic principle of light microscopy. Okay, so the basic principles of light microscopy are actually like simple concepts or relatively simple concepts, but there are many and they are extremely important, and they are all of them linked together, and they have consequences related with all the techniques that you will use afterwards, from confocal to light sheet to photon, super resolution, everything that you will do, okay, because they are related with the image formation principle. So whenever you don't understand, or you forgot, or you are missing the link, please ask, and I would like that this was a very interactive bi-directionally exchanging lecture, okay? All right. So I will give you some small historical elements of microscopy. It's written a lot of, so basically, so the first instrument that was used to magnify and was implying like more than one single lens is attributed to the Zachariah Jensen and his son, and it was made around the 1590s. So, but then the first person who truly made a compound microscope was Galileo Galilei in 1609. And the term microscope was actually used for the first time in 1625 by Giovanni Faber, an Italian who used it so to basically, so he used the two Greek words. It was microscope, which is like a small, and scope, like the mean to image. So the mean to image small things for this instrument. It was never used before. Okay, and he used it. He made the term. He invented the term for Galileo Galilei. And then, for the very first time, so it was Robert Hooke, a British scientist, who actually used a compound microscope. So compound means that he was using at least two lenses, okay? So with, and they need to get used to this, sorry. So he improved the way of illuminating the specimen, because he was not just using a lamp, an oil lamp, like an oil candle, but he used actually a glass bulb filled with oil to focus the light on the specimen. Okay, illumination was a really difficult thing at that time. And then he used his microscope to publish a book that is called Micrographia, where for the first time he used the term cells to describe the structure of this vegetable tissue. And why he used the term cells? Because he saw these structures that are like tiny squares that were reminding him actually like the cells of monks in monasteries, okay? And it's from that on that we start to use the term cells. And But anyway, it was actually Van Leeuwenhoek that in 1675 approximately, he developed this kind of microscope. Okay, so this is a very tiny microscope. It was small like a thumb. And it has one single lens there, and this pin here, where the sample was attached to, and then he was holding it against light right in front of his eye, and he could see things for the first time that nobody has ever seen before. Okay, so because these lenses were capable to magnify enormously for the time, like 200 times, and he saw for the first time and described sperms and bacteria. And there is no doubt that he could see them, because nobody has ever seen those structures before. So there were no drawings available. There was nothing else. And look how precisely he actually drew them. So, and bacteria, they are even smaller than eukaryotic cells. I guess you have an idea about this. So it's incredible. And it's even more puzzling how he could make lenses that were so free of inclusions, so smooth on surface and well grounded, but so tiny that could observe specifically the structures and of such a small size. Actually, when he died, so this secret died with him, because nobody knew how he did. Okay. And then finally, in 1873, Ernst Abbe, a German scientist, he actually laid down the scientific basis of image formation. He really understood how images were formed, and he mathematically described for the first time the resolution limits of a lens. And he also laid the basis for making the lens process, lens grinding process, not a trial error process, but a mathematical or scientific driven process and reproducible. He joined Carl Zeiss together with Otto Schott, and then they all together developed numerous optical instruments, but really a lot, including the apochromatic lens, of which you will hear more also regarding. So he used for the first time the terms numerical aperture, he defined resolution, and all these things that you will learn about in this lesson, if I manage to convey the message. And by the way, Ernst Abbe, so I'm the head of the ABBE platform, and this is not a case. So I gave the name to the department, microscopy department of the Champalimaud, so to make like in tribute to the great scientist. So all our lenses, all the objectives, all the microscopes, all the telescopes, your eyeglasses, phones, and everything that we used and that use lenses are designed accordingly to the creations of ABBE. Okay. This is to tell you that if you don't know the resolution limit of ABBE, when I will ask you, I will be very disappointed. Okay. Okay. And then, last but not the least, in 1893, approximately, August Kühler invented Kühler illumination, because at that time, still the problem of evenly illuminating like the sample was huge, because there were lamps, and then the filament of the lamps were basically imaged together with the specimen. So there were structures brighter than others. There were shades projected on the sample, and illumination was full of aberration and not uniform. And then August Kühler, it was his PhD project, when he developed a set of lens to actually perfectly defocus light, or like a perfectly defocused image of the filaments of the lamp on the specimen. So basically creating a uniform illumination, sending parallel lights. We will do some ray optics, and then I hope you will clear by the time what is a perfectly defocused image. Okay, so then we use light to image our specimen, right? But what is light is a little bit difficult, huh? Okay. And light is actually an electromagnetic radiation, and that is part of the electromagnetic spectrum, and that it goes from approximately 400 nanometers in wavelength to 700 nanometers in wavelength. Okay, this is the visible portion of the electromagnetic spectrum. There are people that are a little bit more sensitive to the UV or to the near-infrared light, but more or less is this 400, 700 nanometers, where the 400 nanometers corresponds to the purple blue color, and then the 700 nanometers to the orange, red, dark red colors. Okay, so this is a super tiny portion of the electromagnetic spectrum, but it's extremely tiny. It's so tiny that this proportion here is not correct. Okay, because the electromagnetic spectrum goes from gamma rays that are whose wavelength is extremely small, so it's in the order of picometers, and to radio waves and that are like can be in the order of the meters or even kilometers. Okay, so and then we only see the super tiny portion, so less than 400 nanometers in difference between 400 and 700, maybe 750 if we're really good with the rise. But why? Have you ever wondered why we see only this fraction of the electromagnetic spectrum? And almost the majority of all the creatures that have like a vision have like they are sensible to this portion of the electromagnetic spectrum and not others. So the answer is here, and it's the fact that light developed underwater, and then the water absorbs the majority of all the wavelengths almost completely, except, so there is a depth, like a trough in this absorption curve, exactly in correspondence of the visible spectrum. So basically, when organisms were evolving underwater, the only portion of the electromagnetic spectrum that was available and that was not fully absorbed by water was just like this tiny portion here, like approximately half microns in wavelength. And then that's why our eyes and the eyes of all the other creatures, almost all the other creatures on Earth, developed to be sensitive to this portion of the electromagnetic spectrum. Is it clear? Yeah. Okay, that's good. And then I need to do a little bit of back and forth just to make sure that we are all on the same page. So I told you that this is like so light is an electromagnetic radiation, and it's represented like a sinusoid. So this is a sinusoidal representation of light, and we need to do some nomenclature. So the wavelength that I was telling you about is nothing else than the distance between two adjacent symmetric points, so like two trough or two crest or peaks. Okay, so then the wavelength will be this distance in this representation, or either this distance. And we have the crest, which is the peak here, the trough, and the elevation of the crest, so with respect to the average in propagation, so in energetic average of the electromagnetic wave, is called amplitude. Now, I'm telling you this because in certain circumstances, so when two or more trains of waves that are coherent, so that's why it's in certain circumstances so you will hear probably a few more about coherent light. So in certain circumstances, so two waves can actually interact, and this is called interference. The interaction is called interference, and this interference can be constructive or destructive. Let's have a look at constructive interference. So here we have like a green sinusoidal representation of light, and then a magenta one. And then if they were capable to interfere, so let's consider them coherent, So they will generate a resultant that is a third wave that will be basically the mathematical sum, or like, let's say, the arithmetical sum of these two waves in each single point. So if we consider here amplitude 0 and amplitude 3, it will still do 3, so 0 plus 3, 3, okay. Then 0.5 plus 2.6, it will be 3.1. 0.87 plus 1.5 will be 237, and so on, point by point. And so generating like constructive interference, increasing, for example, the amplitude of the resultant wave. And consequently, in a very similar manner, so I did 2 clicks as usual. So if you have like two wavelengths of equal amplitude, but shift, so a peak or crest corresponding to the trough of the other one, so then summing these two waves, you will have a resultant that is completely 0, okay? So, and this is the maximum example of destructive interference. Okay, of course there is like there are gradients, so you can have like more or less constructive and destructive interference. Okay, and is this all clear? There are no doubts about this. Very simple, right? Okay, so I was saying that we use light to observe our specimen at the microscope, but then we need to do also some nomenclature about the microscope, otherwise we will not know what we are talking about. So these are an upright and an inverted microscope. For sake of simplicity, we will simply say that an upright microscope is a microscope where the objectives are coming from the top, okay? And an inverted microscope is a system where the objectives are coming from the bottom, all right? It's not true. I mean, it is true, but this is not the reason of the name. But let's say we stay with this for, otherwise we need to go too much in depth. Okay, so let's consider, so we start, when we observe or study an optical instrument, we always start from the source of light, follow the light, and then you will find every single optical element or a structure of interest, and you will not get lost or confused. So this is a very important tip that I'm telling. So let's start with the lamp house here for transmitted light, which is the light that is usually used for bright field imaging. Okay. So then, in an upright microscope, the transmitted light lamp house will be at the bottom, in an inverted system at the top of the system. The light will travel, there will be a mirror here, and will be directed towards this unit here, which is actually the condenser unit. And it will be the same in the inverted system. The light will travel and will be directed to the condenser unit, which will focus the light on the stage where the specimen should be, okay? And we will bring up and down our stage with our focusing knobs. Have you ever done this at the microscopes? Okay. And then the specimen will be observed by the objectives. And then the light the information will travel up either to the eyepieces, and in this case, it will travel here. Okay. So through the camera ports, for example, in a wide field system. In a confocal, there will be another device that is called photomultiplier field. And okay, then when you do fluorescence, you have instead like an epi lamp or epi illuminating lamp, and that is like from 100 to 1,000 times more powerful and intense than a transmitter light lamp, and it's used to excite your flow, of course, and collect your fluorescent signal. And you all have this experience approximately, right? So in this case, the light will travel in this direction, will go through the objective that will focus the light on the specimen. So the objective in fluorescence, or let's say epi illumination, will work as the condenser in transmitted light that focus the light on the specimen from the bottom. Okay, so then your fluorophores will be excited. You will learn more about this later. Then the emitted light will be collected by the objective and then sent to your device, acquisition device, or to the eyepieces. And it's the same here. So the epi lamp will send the light through the objective, they focus on the specimen, then the emitted light is collected back and go to the eyepieces or to your camera. All right. So there are two things missing. What are they? One, I already mentioned. I cannot wait too long because we have to do like 200 slides, guys. We have only 3 hours. So,
would it be the sample?
Very good. So specimen is the very first thing, but there is one thing that is open that is still missing. Who has an idea? One attempt allowed for just time reasons. Yeah. No, the PMT is like a specific detecting device for confocals, which will correspond to the camera in a white field system.
The diaphragm?
No, so then what I'm talking about is actually the brain. And then it's not a joke. So your brain is really important. Why? So why is the brain important? It's really serious. So, and here there is an hint to the answer. What is this? Tell me.
Picasso.
Hmm?
Picasso?
Yes, but then what do you see there? What is the subject of the painting?
Two perspectives. You can see a profile and also front.
Yes, but what is represented here? It's a woman. Okay. And then we recognize that this is a woman. But do you see that there is something wrong with this, like painting and then an actual real woman? I hope you understand this. Okay, so basically this is just to tell you that when we image something with our microscope, so we image our specimen, we look at an image of the specimen and not the specimen itself. Okay. So in other words, we look at a representation of the biological specimen. There is a kind of like a likelihood or like a possibility of what actually the specimen is. And it's full of aberration, it's full of limitations, and it's clearly different from the original object, and it will differ. The very same specimen, the image of the very same specimen will differ from one microscope to the other, and accordingly to the labeling that you do, or like the techniques that you use to observe it. So that therefore we need to understand so image formation, its limitations and aberrations in order to correctly interpret. Because if we look at Picasso, if we were aliens, we looked at Picasso image of a woman, and then we when we say, okay, these are women on the earth, then we will have a really wrong idea of who, so what the population of Earth is, right? So, and these are very common mistakes of beginner microscopists, that they look at the image and they say, this is my sample. And it's not, it's an image of your sample, okay? And it's exactly like Picasso's woman. Okay, so your brain. Let's try to learn about all these things, limitations and so on. So what a microscope needs to do is providing resolution, contrast, and magnification. So now, what is resolution? Resolution is the ability to carry information about the fine details in the specimen to the image. Okay. Contrast is the difference in the image between features and their surroundings, which means, for example, there is very little contrast between my t-shirt and my shirt because they have the same color. So you almost don't see where one starts and the other ends, right? And so you will see it's extremely important to be able to distinguish between foreground and background. Okay. And magnification. Magnification because we need to make the image large enough to appreciate these tiny details, okay? Okay, but if the tiny details are there, magnification will be completely empty. you can enlarge an image enormously, but then if you see only square pixels in your details, then magnifying will not give you any further information, right? All right, so let's have a look. Resolution. This is like a sentence from Peter Evenet, so who is a senior microscopist at the Royal Microscopy Society, and I had the honor to have him as a mentor for many, many years in my life, and you will see him in a movie that we recorded at the Max Planck together later, like just 10 minutes. And I actually sent you the entire movie as a material for the preparation to this course. And if you have the link, I will really recommend you to watch the entire movie. So he said resolution is the most important property of a microscope and the most difficult to achieve. Okay. He was very absolute in this. There are lots of things and lots of consideration could be done, but this is his sentence, and he is partially right, of course. So, but what are the limits of resolution, and what are the factors that set these limits? So the ultimate factor that sets limits to resolution is diffraction, okay? And diffraction happens at the specimen and at the lens. All right. Do you know what diffraction is? So what is diffraction? It's one of the most difficult, and don't worry, it's fine. So I understand, I understand you guys. So, but then, let's do a demo. Laser and wire. So I have some laser here, and this is the 635 nanometers laser, so it's red. And I have a wire here. It's a very thin wire, very thin. Okay. So, and I will shine this light on the wire. So, before I do it, I would like that you told me what you expect as a result. I will go actually later, so you will see the result a little bit enlarged. And I'm really sorry because we in back might not see very much. So, but I will do it from here. So there, do you see it? So I'm creating like a spot of light. Okay, now I will put the wire in front of the source of light. What do you expect as a result? I need an answer. Hopefully wrong. What would you see? Spread. Somebody else that has a different idea? I need a wrong answer. So, no. If nobody thinks that we will have like actually like a spot divided in two spots like this, for example. So this is like the before wire, and then this is like the after the wire. I hope that somebody thinks that this will be the result. Please don't be shy. Who thinks that this might be the result? The wrong answers are the best, guys, because then you can actually say, yes, yeah, then it's wrong. Fantastic. Now I can show you what is the reality. So nobody thinks about this. So as this idea. So, so I will show you. So the spot, and then put the wire in front, and it's very easy to see. Okay, you see it? So we still have a spot. So the light is not divided in two. It's actually even brighter than if I remove the wire. And then there is like what is called diffraction pattern. So several dots that are like white, dark, and so sorry, bright, dark, bright, and so alternated and symmetric. Do you see it? Okay. So there are two observations that needs to be done about this demonstration. So the first observation that we don't generate this. That I know that somebody thought about this. But we do not generate this, although we are placing an obstacle in front of the light. So the light doesn't diverge, and then it doesn't create a shade in front of the object, so behind the object actually. So, and this is a property that is like typical of water and waves. So I will show you here two observations. The first observation is the light bends around the corners, and as there is like a train of waves that is parallel to this aperture here, there is then propagating in a curved manner, and it's actually cover the angles, so that will be in shade if the, let's say, white or water will propagate like as a straight line. Okay, so then light bends and actually goes around the obstacle. And if you put like as an image, you could think about like placing like a pole or like a kind of a vertical structure in a river. So the water will fill the space behind the river. So it really bends around. And the other thing is that there is a diffraction pattern, right? So this. Okay. So why there is a diffraction pattern? So the reason is, so if we have one single source of light, so then we will generate like this electromagnetic, so the electromagnetic wave, so light will propagate in this way. So this each of these semicircles represent actually a crest, and then you will have a trough, another crest, a trough of the waves that are propagating from this source of light. Okay, and this is the wall. If we had one single source of light, we will just have light on the wall. But then when we use the wire, we are splitting the source of light into creating basically virtually two sources of light. And since they come from the very same source, they are coherent, so they can interfere. So, and when we have a second source of light that generates, so this waves in phase with this, so then we will have troughs that will correspond to other troughs generating constructive interference, and trough that will correspond to the middle portion of the, so to the, so crest that will correspond to the trough of the other one, so generating destructive interference. So then, if this is our pattern, I will show you. So in the middle here, we have crest with crest, crest with crest, crest with crest. So we have actually a really bright spot that is even brighter than the light that we originally shine without the wire, because we have constructive interference. And then immediately to the next to it, we have this crest here that is in correspondence of the trough of the light generated by this source. So you see that it's in the middle between two crests. So this will interfere destructively with this trough. And since they are equal, because there is the same source of light is split in two, they are of equal amplitude. So they will generate basically complete darkness. And there is a gradient, you will see, so it doesn't become completely dark. So it gets completely, so it goes into darkness and then comes out from darkness. And then it will repeat in the same way. It will be so constructive interfere, destructive, and this is it will generate the whole pattern from one side and the other side. Okay, I don't know if you have doubts about this. I see some puzzle face. Do you have questions? It's really very simple, probably. Okay, perfect. So we have the bending of light, and we have a diffraction pattern, so interference. So now that we experience these two things, we can read together. So the definition of diffraction that I modified from the dictionary. So Diffraction is the bending of waves around the corners of an obstacle or through an aperture into the region of geometrical shade of the obstacle aperture. And we saw this. It's true. So it's the bending of light. Perfect. Okay. The diffracting object or aperture effectively becomes a secondary source of the propagating wave. So because we generate basically two independent sources of light. Therefore, diffraction is typically accompanied by interference between the waveforms produced. And we saw also the interference. Now, reading this definition makes sense in our mind because we experience it, right? So I hope that you will know now what diffraction is. And then I prepare a second demo because it's not, that's not all. Okay, so this, I have two magic wires. Okay. And I will take a green laser now. Okay. Just because it will be easier to see for our eyes. Also the red and the blue. You see the green spot? It's very strong, right? So I put the wire in front of the green spot. Who thinks that we will have that? Okay, guys, fine, perfect. I believe you now. Okay, so I will put, so these two wires have different dimensions. Okay, so let's have a look to the first wire and the first diffraction pattern. Do you see the diffraction pattern? Perfect. Memorize it. Okay. Now I change wire. And I'm using a different dimension. Okay, you see the spot. I'll put the wire in front. Do you see the diffraction pattern? Okay. How does it look? So tell me, what's the difference between this and this? It's really important because these are all consideration. Okay, do you see this? Okay, so how is this diffraction pattern with respect to the previous one?
In the same length, you have more spots when you divide it with.
Yes, in which one? In this or in the other one?
This is
in the figure one.
less spots.
This is less spots. Okay. Wait, and then?
Yes, more spots.
Okay, so wait, because I exaggerated. Okay, so more spots here. And the distance, what about the distance? So that's because there is a higher frequency of spots, right? So the distance between spots is smaller. Okay. Which one do you think generates so the larger diffraction pattern, the smaller, so the thinner wire or the thicker wire?
The larger diffraction pattern being the one with less spots. Correct?
Yes, but this is not the question. The question is, which thickness of the wire will generate the larger diffraction pattern, the thicker or the thinner?
The thicker.
Okay, that was 50%. You got it right. It's true, and so it's extremely important that you absorb this experience. So smaller features will generate larger diffraction pattern, and bigger feature will generate smaller diffraction pattern. Okay. This will have will acquire enormous importance when you will understand how images are generated, okay, and why there is a certain limit to resolution, and because everything depends basically on diffraction, eventually, not completely everything. Okay, but so Peter Rennert was not so wrong after all. You will understand it. Now let's try to change wavelength because there is a second observation needs to be done. So the first observation, what was it? Smaller features, larger diffraction pattern. Larger features, smaller diffraction pattern. Now let's observe the very same wire with two different wavelengths. So I'm using the thinner wire, which doesn't really matter. So do you see the diffraction pattern of the red light? Okay. So contrast is very important. Okay. Memorize it. Try to memorize it in your mind. And then I will go with the green light. What do you see? What do you see? More spots. So what does it mean? So I will show directly. So again, the red. It's more spots, but what does it mean? It's more spots. So rotate in a more precise way. So describe the a little bit more precisely, please.
That the wavelength has an impact on diffraction.
The diffraction pattern is bigger when the wavelength is shorter.
No, it's shorter.
So this one. So look at the distance between the bright spots in the diffraction pattern. Okay, and look at the distance here. Okay, is this larger or smaller than the one that we had before? And then for those of you that have very good eyes, okay, we can try with the blue light. It's really possible to see, but if I go really close, you will see, and if you come very close to the wall, you will see. But basically, there is a difference in size of the diffraction pattern, and this is really obvious and evident with a very short wavelength. Do you see how tiny the diffraction pattern it is here? It's so tiny that who is far away doesn't see it at all. So, but if you do you see it? Any of that you see anything there?
Barely.
But anyway, even between green and red, it was possible to see. So you said more spots in the green and less spots in the red. So then the observation is that with shorter wavelength, the diffraction pattern is smaller. Okay? So shorter wavelengths, they bend more than longer wavelengths. And this is extremely important. I'm missing one of the exactly super important tools. And yes, ordering the hardware platforms to get like okay. So the two more observations are that the diffraction pattern size is inversely proportional to the object size. Okay, and we saw it. So thicker wire was generating what?
More diffraction pattern.
Exactly. Okay. So and then smaller wire was generating a larger diffraction pattern, and then the short wavelengths, so the purple blue light, are diffracted less than the longer wavelengths, okay, like orange red lights. And in fact, we had this effect that you could see with the green. So the diffraction pattern was in green was actually shorter, and there were more spots than when doing with red. And with the blue light was so small, it was almost impossible to see and very little contrast. Okay, so this is very important. And so larger features, smaller diffraction pattern, shorter wavelength, smaller diffraction pattern. Okay. Okay. The image of a point is not a point. This is philosophy, guys. Why I'm telling you this? Okay. Because of diffraction, okay, when we image a dimensionless source of light, that could be one of your floor force or anything that is like tiny and then emitting light, or even like reflecting light. So the image of our source point of light, it will not be a point, okay? But it will be actually diffraction, so will be limited by diffraction, and we will be actually a disk of light surrounded by bright and dark rings, like this one. So here we will have our original object. This, like, let's consider is a dimensionless object. This is not truly dimensionless, but let's consider dimension it. And then we will see it at the microscope actually like this, okay? So where this disk of light is called airy disk, okay? And we have then a diffraction pattern around with circles of darkness and light. And it's called airy disk because it was described for the first time by George Airy, a British scientist that lived in the mid-1800s. So basically, the size of the disk depends on the wavelength, as we observed, okay, and of the image radiation and the aperture of the lens. This is something we will study and we will understand in a minute. So more on this in a few. But the important thing to remember in this moment is the larger the aperture and shorter the wavelength, smaller the disk. So which means better resolution. Why? So let's see this. So first of all, this is an example of the same tiny dot imaged with an objective lens with a small aperture and or longer wavelength, and image with an objective lens with large aperture and or shorter wavelength. So you see the size of the disk is different and the diffraction pattern is different. Okay, so when you see shorter wavelength, smaller diffraction pattern, and also larger numerical aperture, longer wavelength, larger diffraction pattern, and small aperture, larger diffraction pattern. Now, just remember the diffraction, of course, also the specimen, just do not forget. And then you might already guess that if we have two objects, okay, two sources of light that are getting progressively closer and closer together, so there will be a point at which we will not be able to distinguish between the two of them, okay? And if we are in this situation, like this, okay, because of this like disk and diffraction pattern, so we will look at something like this and we will not know whether it's generated by one single source of light, so one object of interest, 2, 3, or many more. So, and this should give you an hint about what resolution is. So can you give me now better definition of resolution? The distinction between 2 points, actually you're not far from full correct understanding. So in fact, resolution is actually a minimum distance, and it's the minimum distance at is the minimum distance at which two objects or two sources of light can still be seen as two separate objects. Okay, And below that critical minimum distance, we will lose the capacity to resolve them. So we will not distinguish them, we will not take them apart anymore, okay? So resolution is a minimum distance. All right. Of course, smaller the resolution, so higher the level of details, because then we will be capable to distinguish tinier and tinier details. Okay, after this, 1 minute break, which doesn't mean that you can do whatever you want, but we can. Do we have questions? Like anything that was not clear or you have a doubt about all these things? Are you very tired? Can we continue? Fantastic.
I have a question.
Yes.
I don't know if it's a silly question, but
There are no silly questions. It's true.
Regarding this resolution, we were talking that smaller wavelengths lead to smaller diffraction.
Exactly.
So if we have 2 points with different wavelengths, how this affects the resolution? Will be able to distinguish them better, or
So if you image them with a shorter light, you will resolve them better, because the diffraction pattern I will show you. So this is our short wavelength, actually very short wavelength, blue. Okay, and this is our long wavelength, red. Okay, since the diffraction pattern and the iris disk depends on the wavelength, and longer the wavelength, larger the diffraction pattern, and shorter the wavelength, smaller the diffraction pattern, you will be still able to distinguish these objects when they will be at approximately this distance, okay? But if they were the same objects, let's imagine the same protein of interest in the same specimen, labeled with a different fluorophore. It is, for example, redshift, Alexa 4647, CI5, or even CI7 and longer wavelength, then having a larger disk and a larger diffraction pattern will imply that you will see them, you will still distinguish them at this distance, which is much larger than this one. So imaging the very same object with different wavelength implies difference in resolution. Okay, is it clear?
but when we combine, for example, one wavelength and one blue one?
So usually you will separate in that case in time. What does it mean? That you see first one and then the other. So they will not be present together at the same time. So you are distinguishing because of this. Okay. Okay. So then let's continue. And what about refraction? So we talk about diffraction, but also refraction exists. Maybe there might be people denying refraction. It's true. So there are people denying that the Earth is spherical or approximately spherical. So if you're not like a refraction denier, we can discuss refraction also. Okay, so what about refraction? This time we start with the definition, and it's an heavy definition to understand. So refraction, phenomenon of light, radio waves, etc. It doesn't matter for us, it's light being deflected in passing obliquely through the interface between one medium and another, or through a medium of varying density. So really seriously. So let's read it together again. So it's a phenomenon of light being deflected. Okay, so there is a deflection of light, which means a change in direction. Okay. When passing obliquely, this is not of little importance, okay? So because this phenomenon of changing direction of light is related and depends on the angle of incidence of light on the surface that separates the two media, okay? so passing obliquely through the interface between one medium and another, or through a medium of varying density. So one medium and the other, why one medium and the other? Because we need a difference in density or optical densities of two materials. Okay, so for example, air and water, glass and air, glass and water, and so on. Because if light propagates within just one medium, then it will just progress at a certain speed. Okay, so we need a difference in density of the material. All right, so let's have a look. Then, so we can talk about refractive index. So when light travels into vacuum, it travels with a speed that is equal to c, which is the speed of light, okay, which is approximately 300 millions of meters per second, 297 something. Okay. Light is slowed down, and I place this within quotes because quoting marks, because light in reality doesn't slow down. Okay, so the speed of light is a constant. You have to know this. But the fact is that there is an atomic interaction between light and the atoms or the molecules, actually the electrons of the atoms or of the molecules constituting the medium, the transfer medium through which it's passing. And then it's like passing, doing an atomic interaction, vibrating, then going again to the next molecule, and then interacting, going to the next molecule, interacting. But the speed between one molecule and the other one is always the speed of light. Okay. Okay. The amount by which it is slowed down is called refractive index. It's indicated with n, and it's a fraction. So it's equal to the speed of light in the vacuum divided by the speed of light in that specific medium, and necessarily must be bigger than 1. Okay. I also placed there 1, so equal to 1. It's not true. So it must be always bigger than 1. But I also placed bigger or equal because the speed of light in air is always approximated to 1, because it's very little difference. It's, in reality, it's 1.0003. Okay, so then everybody considers 1. All right, and there are like few examples of refractive index. So the refractive index of air is 1 approximated to the third decimal number. Okay, water is 1.334, glycerol and oil. Okay, and then you see, the denser the material, larger is this number, because the speed of light in the medium becomes smaller. So it becomes slower and slower and slower. Then in a fraction, if you decrease the number that you have like at the denominator, the result becomes bigger. Are we okay with this? Okay, very good. So so the slowing down of light has a very important consequence, which is the bending or the change in direction of light when it passes from one medium to the other. And there is here this asterisk, because I already told you that this is related with the angle of incidence. And then we will do some demonstration about this. Let's see. Demo coin in the cup. Okay. So for this, I will need some action from your side, because we will need to make this experience. Unfortunately, there is not a projector that can show you this. Oops. So all the guys that are in the first 2 rows will need to come here to the table for this, and then we do the other 2 rows, and then the last one. Okay. So please stand up and come here. So we have a cup with a coin. Do you see the coin? There's a coin glued at the bottom of the cup. So please come close until you actually can see the coin in the, so you have to be here to see the coin. So more or less at this distance. Have a look. stay straight. No, you don't have to. So I'm asking you not to just look and then, okay, there's the coin, and then you leave. So you have to look at the coin and stay still, and please reach the distance from which you can see the coin. And if you cannot come from this side and come closer, you can come from this side. I don't need to be there. So turn around. Do you see the coin? Maybe we can put it even closer to the center. Do you see the coin? Go there. Those people that cannot see the coin can do another turn. So then we change, and then we still stay there. Maybe there are too many people. We do one more turn. So, but you have to look at the coin and stay in a position where you look at the coin. So look at the coin and keep all your position. Please. Do you see it? Oh, okay, now go back. So I move like just enough to not see, look at the coin anymore. So keeping the position of your back, just move back of your, so stay straight, and then move back just enough until the coin disappears from the edges. Are you there? Okay, do you see, are you in a position where you just not see the coin? Okay, now I will pour water in it. Don't change your position and tell me what happened.
Now I see
You see the coin, yeah. Very good. Okay, so this is very important because now we will do this experience. Did you see it? So please come here. Maybe we do just one row per time. Come around. Do you see the coin? Okay, then move back just enough to not see the coin anymore. Are you seeing the coin? Very good. And you?
No.
Okay, and then I put the water. Do you see it? Does it appear? Perfect. Very good. So something changed. Okay, perfect. Next row. With all this exercise, not of the breaks are needed because they okay, please come around here and then just do so. Assume a position like around the beaker here until you see the coin. Do you see the coin inside? So stay closer, come closer. Do you see the coin? Okay, and now move back just about, just the right distance to not see the coin anymore until it disappears just behind the edge of the cup. Are you okay? You don't see the coin, right? Perfect. Then I pour water. Do you see now the coin? Does it appear? Perfect. Very good. So experiment is successful. So, and then let's do it again for your colleagues, and then I will explain. Guys, next row of people. You heard it already 2 times. So come around here, and then just like, but you need to be able to see the coin. Please come close. No, you have to come much closer, you guys. Otherwise, we do it in 2 turns. Okay. So please come also on this side. Maybe you can do. And if you don't see it, we do. Do you see the coin inside of the cup? Okay, and now move just back. So in the position that will not allow you to see the coin, when the coin it just disappears behind the edge of the beaker. Okay, so just that position, and then I will pour water in it. Do you see the coin now? And it appears, right? Okay, very good. So this is exactly what the experiment was supposed to make. So something changed to the light that we were perceiving, right? So next people, so next row, is there anybody else? Ah, okay, so then it's good. So this is like one of the most successful scientific experiments ever. You repeat it 3 times in a row and it gives over the same result. So reproducibility 100%. So very good. Okay. So what we did is that we had our beaker or cap with the coin glued at the bottom, okay, and we position our eye just far away enough to not be able to see the information coming from the coin, right? So you see, this light doesn't reach our eye. It's just like it's reaching like just like farther out. All right. Then we pour the water, and what happened was that we bend the light, and we, without moving, we start to observe the information was like not reaching our detector before, okay? Because then the light was coming from the coin, then outwards, and then it reached our our eye. So which means that light bends away from the normal when passing from a refractive index larger, so from a medium with a refractive index that is larger than the refractive index of the second medium. Okay, water is denser than air. Okay, so and then when we do this movement, so when the light passes from water to air, bends outwards with respect to the normal, so the perpendicular here. Okay, and that's why we observe that then we suddenly have information about the coin. Okay, all right. So then, laser and glass, so the observation to be made. I know what was this laser. Ah, yes, no, I remember. So we have a diffraction kit here, and I will use just a green laser here. Do you see it? Okay, and we have some glass. Glass is denser or less dense than air. Okay, so good. Okay, so then we expect light slowing down when passing through glass, right? All right. So, and then what happens here?
Nothing.
Very good. Nothing. Okay. So, and that's because light is passing through glass. It is truly slowing down, then it accelerates again, but the angle of incidence is 90 degrees, so it's perpendicular with respect to the surface of separation. Okay, so that's why I told you that this also there must be a difference in the refractive index between the two here, but it's also important that the light is obliquely traveling through the surface of separation. So because it's also dependent on the angle of incidence. And in fact, if I turn this like this, you will see that there is a certain bending of light, and light doesn't propagate straight, it bends. And then what happens here? So it enters, bends, and then it exits. And what does it do?
Return to the initial merge.
Exactly. So then it bends again, so it comes back to the initial direction of propagation. So it means that there is like also, let's say, proportionality that is like reserved when entering from one medium to the other, and or exiting, and then accordingly to the angle of entrance. So okay, that's really good. And then I want to show you another thing. So now this one. So we have here. So do not consider the light path until here. Let's consider that our light is passing from glass to air. Okay. And then what happens is the same thing that happened when the light was coming from the water to the air. So it bends outward with respect to the perpendicular to the surface of separation. So you see we are traveling with a certain angle, and then the angle increases. You see this? Okay. And then the more I increase this angle here, the more it bends outwards. You see? It's bending more and more and more until it travels parallel, which is called critical angle. And after this critical angle, then it totally internally reflects and comes back. Okay. So I will show you again. So the angle of the light that passed from glass to air is larger. So the exiting angle is called angle of refraction, is larger than the angle of incidence on the surface. And it depends on the angle. So how larger it is related, we still don't know, it's related with the angle of incidence. But if I increase this angle of incidence, it becomes larger, and the angle of refraction becomes larger and larger until light travels parallel to the surface of separation, and then it disappears completely, and there is what is called total internal reflection within the medium with higher refractive index. Is it cool? Okay. All right. There are a few observations that needs to be done. The first observation is, so the first observation is that when the light passes perpendicular, there is no change, right? So the angle of refraction is proportional to the angle of incidence, okay? And then when we have an angle that is different from the normal, so then there is this change in direction. And the second observation is that when the refractive index of the first medium is larger than the refractive index of the second, like glass and air, okay, there is a critical angle of incidence beyond which total internal reflection occurs. And we saw it. So we were enlarging the angle, enlarging the angle, enlarging, and then at a certain point, the light was not propagating to air anymore, but it was staying inside of the glass. Okay. And this is mathematically described by Snell's law, which is this very simple equation. So the ratio between the sine of θ1, which is the sine of the angle of incidence with respect to the normal, so the perpendicular to the surface of separation of the two media. Okay, so this sine and the sine of this angle divided by the sine of the angle of refraction. Okay, it's equal to the ratio of the two media. So the media of the second, so the value of the refractive index of the exiting medium, and the refractive index of the initial traveling medium. So the media where the light was initially traveling. So now it's very simple. This is really basic math. And then if you want, you can also write it like this. So N1 sine of the angle of incidence is equal to N2 sine the angle of refraction. Okay? So then, if you have for a given angle of incidence, you want to know what is the angle of refraction, so how much it will bend outward or inward, because it depends on the refractive index of the two media, right? You can say that the sine of R is equal to N1 sine of I, of the incident, divided by N2. Okay. If N2 is 1, like in this case, because we have air, so then this doesn't play a role. So then the sine of the angle of refraction is equal to the sine of the angle of incidence multiplied by the refractive index of the first medium, which is, if its glass is 1.515, so which will make the sign of R larger the sign of I of this factor. Do you understand? So that's why it bends outwards. This is the description, it's not the motivation. Okay, so the mathematical description. And then, of course, you can do all the calculations that you can solve of the case. By the way, all the slides that you will see from now on, that all the bendings of lights and all the animations, they were done with the calculated angles of refraction, that I had lots of time doing, like very much. But it was very cool. It's true. Yes, so they will not be, so they are just not made up. So they are really calculated.
So in that example, if the refractive index is always bigger than 1, right?
Yes.
Shouldn't theoretically the refraction be always outward?
If light is passing from a denser medium to air, yes. So, or from a denser medium to any other medium that it has like a less dense, less density, so less smaller refractive index, the bending is always outwards with respect to the normal. If you are passing from a less dense medium to a denser medium, from glycerol to glass, for example, so your mounting medium of samples might be, for example, like mobile. Mobile is the glycerol base, and glycerol is less dense than glass. And you have your cover slip on top. So in that case, it will bend inwards. Okay? So, and then you also know that there is a critical angle. So for which basically the sign of θ2 will be 1. So that's why it's traveling horizontally the light. And then there will be beyond that angle total internal reflection. Are you okay with this? Okay. There is a very important thing here that you must not forget, and you must not get confused with diffraction. So refraction varies with wavelength, and short wavelengths, so purple blue light, are refracted more than long wavelengths, orange red light. Okay, and in fact, if you remember this picture that has been used since Newton 1665 ever, and then always, and there is also a fantastic album from Pink Floyd that is like it's like this. So you will remember, so that when there is white light incident on a prism, so then you will have this phenomenon of dispersion, and where the different wavelengths will be actually differently refracted, with the shorter wavelengths, violet and blue colors, like closer to the glass or more banded than the orange reddish light. Okay, so and then you see here, so red bends less, travels straight and bends less than purple, that is the one that bends the most. Do you see it? Now, what was diffraction doing with respect to the bending of light in function of the wavelength? Shorter wavelengths were bending more or less? Less. And in refraction, instead, shorter wavelengths are bending more. Okay? So this is extremely important, and you must not forget, and you must not get confused about this. All right. 1 minute break, because we need to. So we can make a consideration with a minute break. Since difference of, okay, there's so many considerations can be done, but I just thought about a super cool demonstration. Where are all my lasers, guys? We're very small. Green and red. Okay. So why so the question is why is like a longer wavelengths, let's say red colors or dark red colors, are diffracted less the shorter wavelengths, blue, purple, violet colors. Why? Okay. Do you have an idea?
Expanding the wavelength longer, they will interfere in longer distances in space. So you will have the diffraction.
So it depends on the wavelength, because that's the difference, is true, okay? And it depends on the atomic interaction between light and matter. But the answer is that nobody knows. So there is no answer to this question, and yet. But there is a common observation in other structures, for example, in other waving, so in other matters that is propagating in waves, like water, for example. So if you look at the propagation of waves in the ocean, okay, and put on blue, where this is a crest, this is the next one, and so on. The common observation is that if you have like a rock in proximity of shore, okay, if the rock is small, like let's say like this, less than half of the wavelength, which is the distance between one crest and the next one, okay, the wave will propagate without being disrupted by the rock. So we did like this, as if it was not existing, okay? But if the rock is larger than at least half of the wavelength of our water in this case, then it will break here, and it will bend then around, and it will propagate like this, and it will interfere with all these things. Okay, we don't know why, but this is a common observation. In the same way, shorter wavelengths, since they are shorter, they more easily encounter structures that will actually be of the same size, or more often, let's say, encounter structures that will be of the same size or approximately the same size of the wavelength or half of the wavelength. So they interact more because of this, and then they are slowed down more and bend more. Longer wavelengths is like people that do like large stacks in a math field, and then they are slowed down much less, because they are slowed down in 3 stacks, they pass the math field, and they are slowed down only 3 times. If you do very tiny stacks, then you are slowed down every single time you step into the math, right? So they interact less because the wavelength is longer, and probably like in a propagation of the wave of the sea. So when there are structures that are smaller, the waves just pass and they start. And because of this, there is actually a cool thing that I didn't plan to show you. Let's see if it works. So we have here 2 lasers. One is blue and one is red. Which one is the shorter wavelength? Blue, exactly. Okay. So if I put my thumb here and I turn on the laser, okay, and the laser is on because you see the light here. You don't see anything, right? Okay. But if I do the same thing with the red light, you see the red light. And that is partially related with this, because there is like the interaction of the red light with matter is less, and then it propagates more, and then you see more. And then there are many things behind this concept, but one of the things that you can also understand is, since it bends less, so you can actually see deeper in your tissue, for example, okay? But this is only partially related with refraction. There is also lots of other things. Okay, let's stop with the 1 minute break and let's go on. Yes. What's the time? So maybe, let me see, because it's 11. So maybe we do at 11:30. let me finish the next concept. If you, it depends on you guys. Are you okay doing like the next concept, or and then we do a nice 20 minutes break? Okay. Okay. Lenses and ray optics. Gosh, we can speak. Okay, so so all the most important lenses in a microscope, and all the time that you find disaster, it means that this concept needs to be taken with a pinch of salt. So there are lots of many other things there. Okay, are anyway positive or converging lenses. So they are like lenses that are cut out of portion of a sphere. They are thicker in the middle, and they are thinner in the corner, and they converge the light in on an optical axis, which is here depicted with this dashed line. Okay. All right. So they identify. I didn't want to do this, but like let's. Okay, it's okay. When there is light that is coming from infinite, so very far away, and then we can consider so the incoming direction of light as parallel. So these rays as parallel. They will focus the light in a point, converge all the rays in a point that is called focus. That will also identify what is called focal plane. All right. Very good. If the light comes from the focus and is collected by the lens, then it will propagate in the opposite direction and will be propagated parallel to the optical axis. Is it clear? Simple? Okay. So then, since these lenses, they are symmetric, so they identify actually two foci, so not just one focus, but two. Okay. And this depends on the direction of light, because if you have like the light parallel coming from the right, then there will be another focal point on the other side of the lens. Okay, that will behave also in the same way as the previous one. So if light comes from this focus, then it will go parallel to the optical axis. Okay, so then we have for each lens front focal plane and a back focal plane that are identified accordingly to the direction of the incoming light. So if our light comes from the left of the screen, so this is our front focal plane, and this is our back focal plane. So if the light comes from the right of the screen, it will be in the other way around, front focal plane and back focal plane. So the front part is the side of the lens where the light is coming from, okay? Perfect. Now, in ray optics, there are three simple rules that you need to remember. Very simple. So the first one is that if you have like an object, this is when your teacher has a passion. So when you have an object and there is some light coming from this object, the object is very far away from the lens, and there is light traveling parallel to the optical axis. So as you learned, so the light will actually pass through the focus. Okay, the focus, the back focal plane of the lens. So the focus behind the lens. All right. Okay. So when you have light that is passing through the front focal plane, of the lens, then the light will travel parallel behind the lens, and we already saw this. But there is one more thing. So when the light is actually passing through the middle of the lens, then it passes unchanged. Okay, very simple. And since there are three rules, I will also add a fourth observation. That is when the object moves. So I'm sorry, the image will be created where these rays are intersecting, and when the object moves closer to the lens, so the image will also move farther away. Okay. So now that we know this, we can go a little bit deeper, and you have to know the lens can do mainly three things that are really, so that we find in our daily life. It's really familiar for us. So they can behave as cameras do, so forming a reduced size real image close to the lens, or they could behave as projectors, forming an enlarged real image distant from the lens, like this one that you are seeing here on the screen. Sorry. Or they could behave as magnifying glasses, so not forming a real image with parallel rays to infinity. I will show you as the word. Okay, let's have a look. So cameras, the scenario of cameras is a little bit more complicated. So let's say richer. So let's consider these three schemes. So where we have our converging lens, so with a defined focal length, which is called f, which is the distance between the focus and the center of the lens, and it's always equal in these three schemes. Okay. In the first situation, okay, our object is at infinity. So then light travels parallel, and you know it will be focused in the back focal plane of the lens. So which means that our image will be in the focal plane. Okay, and will be spread time and in the focal plane. And this is the case of camera landscape. When you take a picture of the horizon, this is what happens. Okay. Then, if your object is still far away from the lens, but not at infinity, then you have like rays of light that will pass through the lens, and they will pass deviated as you learned, and then they will actually intersect behind the focus, the back focal plane, and they will generate a real image that is smaller of the object itself. Okay, and this is the situation of a camera portrait. And when you have instead your object at the magic distance, this is a very important distance, of 2 times the focal length, so 2 times f, okay? So then the object, so the image will be generated exactly and 2 times the focal length away from the lens, so in the back focal plane, and will have the same size of the object itself. Okay, and this one is what happens when you do a macro picture. And this is cameras. All right, but then there is no magnification. In fact, there is no magnification so far. So far, what we saw, it was like a small pictures, real images of objects, and then these real images are always either smaller or of the same size of the object itself. But then, when we have an object that is between 2f and f, okay, so 2 times the focal length and the front focal plane of the lens, so you see our object here is between 2f and the front focal plane of this lens. This is clear. Okay, so in this case, what happens is that you have an image that is enlarged and real in the back focal plane of the objective. Okay, and then when you have, this is what happens with a projector, so you generate an image that is larger than the real object. And instead, when the object is at the focus or in correspondence of the front focal plane of the objective, what will happen? What happens when the light passes from the focus and goes into the lens? That is projected how? We saw it. Straight, so parallel to the optical axis. So the light will pass parallel. So since these rays of light will never meet, so they meet at infinity, so they will not generate an image. It is called so the image, it says it's at infinity, okay? But the information is there. So they carry the information, but they do not create a real image. To create a real image, you need a second lens So for example, the lens in your eyeball that will then converge the rays of light and focus them in your retina, and then you will have an image of the retina, which is exactly what happens with a magnifying glass when you observe. If you observe something small, if you put a screen after the lens, you will not see the image, you will only see white. But if you put your eye, then your eye that has a lens that converts the rays, so it will create a real image in your retina, and that's why you see it, okay? But the magnifying glass itself will only send the light to infinity. So the information is there, but the image is not real. That's why you say the image is at infinity. Okay. And this is what happens with magnifying glasses. And why I'm telling you this, and this is, I think, the last topic of this part. So because in a microscope, and there is an asterisk there, so you know that there is much more. So we have an objective lens and an eyepiece. So this is a simple compound microscope, 2 lenses. Okay. And then we have the objective front focal plane and the eyepiece front focal plane. If we put a specimen here, which is not in correspondence of our front focal plane, because otherwise the image will go at infinity, okay? So, but it's like between 2F and the front focal plane and F, we will generate a real image that is enlarged, and it's called primary image, that if positioned in correspondence of the eyepiece front focal plane, then the information will be collected by the eyepiece. And wait, before to tell you this, so this is like what the projector does. So we are creating an image that is enlarged and real, because the rays converge here. And then here, the information will be collected by the eyepieces. But since this is the front focal plane for the eyepieces, the information will go to infinity, right? So the image is at infinity. But then we place our eyes in front of the eyepieces, and there is a lens in our eyes. This is like the magnifying glass. There is the lens in front of our eyes that focus the light in the retina, and then we have an image in the retina. So our eye is part of the microscope, okay? And now you know that why I'm telling you this, because you have lenses that behave as projector, lenses that behave as magnifying glasses, and so on. And it's a requirement that the fact that the exit pupil is called, so from the eyepiece, it goes, so the image is at infinity, is a requirement of our eyes, because our eyes evolved to observe the light that comes from the sun and from distant objects. So we are very, so it's comfortable for us to see parallel rays of light that is focused in our retina. And so, and then we have the image. So this is how the lenses in a microscope work, right? Yes.
But the image that is from on the retina is not a real image.
It's a real image. So it's a real image when you have converging rays of light, and you can actually project the image on a surface, like in this case. Instead, and then to have that, light needs to converge in the same point, because it needs to interfere. But this is a big thing, I should not tell you this. So if you have parallel rays of light, instead you will not have like the interference, and then light will go just right, and then you will not have an image. So you need to have the rays of light focusing on one point. But the information is there. And then, and this is what our, the lens of our eye does. So we focus the light in the retina, and there we have the image, the real image in the retina. Then maybe what you're thinking about is that there is the brain that processes the information. So then we know if an orange disc, it's a disc, it's an orange, it's the sun. So this is the interpretation of the image, but the image is real and in the retina. Okay, guys, I'm so happy that you are not running for the coffee break. It's fantastic. So please.
But you can take a picture, for example, with our phones or with.
Yes, and that's a real image. In fact, I can create a real image. So then you can look at the image, and it's you have a real image there, right? So, but a magnifying glass does not take a real image. So it's projecting light to infinity, and you need a second lens to focus the light on something. That can be our retina or like a screen. So you need a second lens to create a real image. But the information is there, and it's just in parallel rays of light.
For instance, when I'm looking through the eyepieces, I see the image like.
Only because you have the lens in your
But it's kind of far. It doesn't seem like I see the image.
Because the magnification is smaller than you would like to have, but it's not so. But it's so you see the image because so the light comes at infinity. But if you remove the eyepiece, this is a really cool thing. So you could try this maybe with the help of Pedro and the other people that manage the microscopes here. So when you do a breadth-field image, so you can remove the eyepiece and put a piece of paper in correspondence of the tube of the ocular, but without the eyepiece. And there you should have a real image projected on the paper of so that you put there, you will see your specimen focused, because that one is the primary image sent by the objective that is taken by the eyepiece, and then the eyepiece focus, so it's in focus for the eyepiece, and the eyepiece send it to infinity. If you take the same piece of paper and you put it behind the eyepiece, you will see only white. You will not see the image. But if you put your eye, you will see the image, because your eye requires the rays to infinity. Yes.
So what happens with people that have glasses?
So people that have glasses, they have no problems in this, because eyepieces are, so the only problem is actually the distance between the eyepieces and the eyes, but you can use glasses with the eyepieces. So then if you want to know what about the vision of people, so why people have glasses and what happens, is because the glass that they have so the lens that they have in their eye is not correct. So it's not correctly shaped, or it doesn't move correctly when it needs to stretch or like relax. And then you need a lens to adjust, to compensate for the incorrect shaping or movement of your lens, but to do the same job, to correctly focus the light in the retina. That's it. Break. Guys, you really deserve it. You're the best class there. Okay, guys. So what is the job of an ideal lens? Okay, let's look at everybody this. So, I mean, it's very simple. So the lens should accept as many rays of light as possible from each point in an object. As we saw, so the light was coming from each point in an object. It should accept as many rays of light as possible. To reassemble all the rays from each point at corresponding points in the image, in such a way that the distance traveled by all the rays from each object point to its corresponding image point is the same. So they all arrive in phase. Unfortunately, this is not really the case. So single element lenses suffer of many aberrations, and some of these are spherical and chromatic aberration, and we will see them. So we will see the main three aberrations of each lens. So, and that's why objective lenses they actually look like this inside. So they have like multiple elements. So the most sophisticated lenses, the most highly corrected lenses, they have up to 13 elements. This is one of those. And to correct for all these aberrations. And the correction is never 100%. So you have to know that there is always a limit to this correction. Anyway, the objective is the microscope. And this is a key concept that must be with you for the rest of your scientific career. So all the other parts of the microscopes are there to actually support the function of the objective. So if you have a confocal and you have lasers, detectors, computer, and anything else, so if your object is incorrectly chosen, dirty, broken, or whatever else, misaligned, so your images will be incorrect, full of aberrations and distorted and whatever else, independently from the fact that you have like the most powerful laser available, the most sensitive detector available, or the computer that is capable of great computational power. So the lens is responsible, especially in fluorescence, of two jobs: focusing the light that will actually excite the fluorophores of your specimen, and collect the information that you care about that is coming from the emitted light of your fluorophores. Okay, so if you remove this function from the microscope does not exist. So the objective lens is the microscope. And now I hope you know that it's the most important part of the microscope, and the most important characteristic of the lens is its aperture. And now we will try to understand what it is. So which is usually expressed as a number, and is called numerical aperture. So let's say we have here a specimen, this tiny dot there, and this is our sample holder or glass slide. And our specimen is emitting rays of light, which implies information, okay? So considering that every ray leaving the specimen carries some information about the tiny details, we want to collect as many rays of light as possible. The problem is that when we observe with an objective lens, okay, then we will have some rays of light that will be collected, and some, so like this in this case, and some that will be lost. Is it clear? Very simple, right? Okay. Resolution is proportional to the amount of information collected. Okay, so larger the amount of information, better resolution you have. So therefore, larger this cone of light that is accepted by the lens, which is called actually angular aperture, higher is the level of resolution. But not only, there are also many other implications that we will see. But this is the first one. Is it clear? So larger this cone of light, this angular aperture, higher level of information, higher level of resolution. Okay. So the numerical aperture is mathematically expressed as n, which is the refractive index of the medium through which the lens will look at the specimen, like this. Okay. And the sine of alpha, which is actually the angle between the optical axis or the perpendicular or the normal to the optical elements, the lens that we are considering, and the last ray of light that is accepted by the lens. Okay. So, and sine of alpha is equal to this numerical aperture. So it's really a mathematical description of this angular aperture of the cone of light that is ultimately accepted by the objective lens. Clear? Now, let's make a comparison between, so I know that some of you, many of you actually had already some experience with microscopes, and you might know that there are dry objective and oil immersion objectives, okay? So dry objective are objectives that actually look through air, and we are representing here like half of a dry objective that is looking through air, and this is our glass slide. This is our mounting media where our specimen is, and this is the cover glass or cover slip that is on top, is the thin glass And the proportions of the glasses is not correct, but is needed for like showing how the light behaves inside, okay? And so that since the refractive index of air is 1 and the refractive index of glass is 1.5, so when the light or the information comes from the specimen and will go towards the objective lens, so what we'll do, we'll pass from glass to air. So what kind of bending will do? You should already know. So it goes from a denser medium to a less dense medium. Here. No. So it's faster and it diverges from the normal. So I also was confused at the beginning when I studied these things and I was a student, but remember, when it goes faster, so it passes from denser to less dense, it diverges. Okay? So then it goes like this and then it diverges outwards. Here I highlighted this specific angle of 39 degrees, and this is a real 39 degrees angle, because accordingly to the Snell law, and you could even calculate it at home, then the 39 degrees angle will give then an angle of 72 degrees of a refractive angle of 72 degrees when the light is coming out from the glass and it goes into the air. And beyond this 39 degrees angle, we will actually have the critical angle and total internal reflection. And that's because the sine of 72 is already 0.95. And if you remember, the sine function goes from 0 to 1. So when it's 1 is when you have an angle of 90 degrees. So you are basically at the limit with 72 because you're already at 0.95 sine. So the sine of 72 is 0.95. It's almost 1. So this is the limit of the angular aperture of a dry objective due to the difference in refractive index between glass and air. And it's 72 degrees here, but in reality, we are collecting only the information that comes from maximum 39 degrees plus and 39 degrees minus on the other side from the normal of the from our specimen, right? Because of these different refractive indexes, right? So we are really collecting a relatively small angle of information. So the information comes from a very small angle of propagation of light. Then, if we compare, and this is like the calculated maximum numerical aperture, which is 0.95, because the refractive index of air is 1, and as I told you, the sine of 72 is 0.95. Okay. If we compare with an oil lens, what happens? Oil has the same refractive index of glass, 1.515. And when light travels through one single medium or different media that have the very same refractive index, so same optical properties, doesn't slow down and it doesn't bend. So it propagates in a straight line, and then we can collect a much larger angle of information, so cone of light, and therefore we have maximum numerical aperture that is 1.4. Okay. Now, some of you might make a consideration, and there is also this the usual asterisk here when I say max, because there are more things that can be added and several other things, but we cannot say everything in this course, of course. And unless you want to spend also your whole lunch break with me, which it might still not be enough. Okay. Why is not 72 degrees this angle? Why is not 72 degrees the angle here between 6? If we can observe 72 degrees here, why is not 72 and 67? The evil microscopy. So I will tell you. So it can actually be 72. But if you do the sine of 72 or the sine of 67, the difference is enormously small. So one is 0.92 and the other one is 0.95, and I will show you in the next slide here. So this is like a representation of the sine function. It goes from 1 to 0. Okay, so 0 value, 1, accordingly to the degree, 90 degrees, 180 degrees, 0 degrees, okay. So when you have an angle of 72 degrees, you have 0.95, so the sine of 72 is 0.95. When you have an angle of 67, the sine of 67 is 0.92. So the difference in numerical aperture, if we come back here, between the sine of 0.67 and the sine of 0.72, sorry, 67 and 72 is enormously small, and the numerical aperture will still be 1.4, maximum 1.44. I actually saw objectives 1.42, but you pay back this with shorter and shorter distance between the lens and the cover slip. So smaller and smaller working distance. So you will not be able to observe deeper in your specimen. You have less and less freedom of movement with your lens, or your lens should be much larger than that. And this is another limitation, technical limitations. And in fact, I don't know if you notice that lenses with little magnification and small numerical aperture have really large lens, but when the objectives are higher magnification, higher numerical aperture, the phone lens becomes smaller and smaller and smaller and smaller. So there's these limitations. But one thing that could be done, and maybe Pedro or somebody else who will tell you about some advanced technique like turf microscopy and so on. So when they want to increase the numerical aperture of lens even beyond 1.4, 1.42, they use denser glasses and denser oil. Because if you have an N that is larger than 1.5, even if your maximum angle of acceptance is the same, so your lens doesn't change, your refractive index will give you a higher numerical aperture. Yes?
What will happen if you use the normal glass, but a substance with a higher density than oil? Would it?
This is a fantastic question. Then we will see in the next slide. No, it's not the next slide, but it will come in peace. Okay, so let's do a small consideration before we go to this question. So, why is NA important? So now we are just like summarizing. So in 1873, as I told you, so Ernst Abbe published a paper where he demonstrated that the minimum distance, resolvable distance, which is called d, small d, okay, is equal to the wavelength of the imaging radiation, okay, divided by 2 times the refractive index of the medium through which the lens is observing, and the sine of alpha, where alpha is this half angle, or the angle, let's say, between the perpendicular, so the optical axis and perpendicular to the surface of the specimen that you're observing, and the last ray of light that is accepted by the lens. And what is n sine of alpha if not our numerical aperture? N sine of alpha is numerical aperture. Ernst Abbe was the first one who used this term, numerical aperture, and this made the history of microscopy and optics for this and many other things. And so we can write again his fundamental equation of resolution. This is the resolution limit of a lens that was for the first time translated in mathematical terms or described by mathematical terms by Abbe in 1873. And this d, so the minimum resolvable distance, is equal to 0.5 lambda, so the radiation of the imaging radiation, divided by the numerical aperture of the objective. Okay, so you need to know this by heart. So it's really important. You will need to use it for everything. So for understanding what are the information that you are collecting from your specimen, what is the limit of information, so what you are not collecting, why or how to choose a lens instead of another one, and how to determine the parameters of acquisition of your image. I think that will be explained by other people during this course, probably, or when you will do like some microscopy by yourself. Okay. Resolutions then is enormously important. Sorry, numerical aperture is enormously important for resolution. Okay. It's also important for light transmission. So the transmission efficiency of a lens is proportional to the power of 4 of the numerical aperture. And I will not have the time to go through the equation, but it's very simple, you can calculate. But it makes it very, it's common sense if you think that if you have a large cone of light that can be acquired by the lens, then you have more photons and more transmission efficiency. And if you have a small cone of light, then you have less photons and less transmission efficiency. And this will make the difference, for example, between observing faint elements in your specimen and not. So being capable of observing or not. So, which is not necessarily related with resolution. So if you, for example, do a single molecule detection experiment and your molecules are sparse, okay, the resolution limit of your lens is not actually the bottleneck of your observations. Because if your molecules are far away and the distance, although they are tiny, if they are far away and the distance is larger than the minimal resolvable distance, you will see them separated and you will be able to count them. So even if you have like a relatively small numerical aperture lens, if they are sufficiently far apart. The problem is that when you have single molecule or fluorophores attached to single molecules, the amount of photons that they will emit is extremely small. So then a large numerical aperture will give you the possibility to see faint signal coming from single molecules, for example, or not at all. And you will see, so you will have an enormous difference in observations, and you might see single mRNA molecules with a lens, for example, 20x or 0.8 lens. This is already like a big hole. Let's say an annoyed 1.4 lens and a 10x or 0.45 lens. Although they might be sufficiently apart to discern them with a 0.45 numerical aperture lens, a small aperture lens. So transmission efficiency is it's a very important parameter. It's directly proportional to the power of 4 numerical aperture and inversely proportional to the magnification. So M is the magnification here to the power of 2 of the magnification. This is important that you remember, because if you have 2 lenses with the same numerical aperture and different magnifying powers, then you have to know that higher is the magnification, less light will pass through. Okay, which might be counterintuitive, because usually people think, okay, a larger magnification, the better it is. And it is better in certain cases because you enlarge the image more, and for certain systems is needed. But if it's not needed, then you are just losing lots of light. Okay, so then the other thing is that the numerical aperture is also inversely, so that it's important because the depth of field of the image is inversely proportional to the power of the numerical aperture, the power of the numerical aperture. But what is depth of field? The depth of field is the amount, the portion of sample that is in focus along the z-axis in one go. So larger the numerical aperture, thinner and thinner is what is called the optical section, or the portion of the sample in focus in one single moment. And this might be a benefit or might be also something negative. Because if you want to observe, for example, a brain slice of like 50 microns, and you are using a wide field system, if you use a 20x lens, that has a depth of field of 1 micron approximately, you will see lots of blur because you will have in focus a single micron, and then all the almost 49 microns that are above and below the focal plane, they will contribute with blur to your image. If you use a 5x lens that has a depth of field of 50 microns, you will see everything in focus and the image will look all sharp. So this is another consideration that needs to be done. What about magnification? So magnification is, before I tell you, it depends on, you already know, because if you remember the ray optics, you remember that placing the object between 2f and f, it will give a real image magnified, okay? So in really poor terms, or let's say pragmatic terms, magnification is the capability to put so in focus as close as possible to the lens. Okay, so it depends on the focal length. And if you look at your thumb, let's do this experiment together. You put it away, so you put it far away and look at your thumb. When you get closer and closer and closer and closer, your thumb will appear growing in size. This is magnification. So we are magnifying our thumb with our lens, okay? Because we move it between 2f and f, and then the closer we bring it to f, the larger the image is. And shorter the focal length, the larger you can magnify. In fact, the magnification depends on the objective focal length, so shorter, higher magnification, and then on the position of the object between 2f and f. Object closer to f, higher magnification. But if you put it in f, then you don't see anything anymore, because you will not have a real image anymore, and you will go to infinite. So you will have an image to infinity. And then magnification and numerical aperture are not necessarily linked together. So these are two completely independent parameters of a lens. And very importantly, the resolving power of a lens does not depend on its magnification. Okay? So this is something that might turn your world upside down, but it is true. And if we come back here to ABBE, so resolution depends exclusively on the wavelength of the imaging radiation and the numerical aperture of the lens. There is no magnification curve, magnifying curve, okay? So the only thing that is important is actually how much information is collected, so the angular aperture of the lens and the wavelength of observation. All right, so if you have two lenses that have the same numerical aperture, they will have the same resolving power independently whether one is a 10x and the other one is a 100x. And actually, if you have a 100x, you will suffer of a loss of transmission efficiency that is monstrous. Okay. Then we said this. This should be carved in stone in your together with the resolution equation about that. Okay. Now it's time for a small movie. So Pedro, maybe I need your help to switch here. And so we have so it's time to put together all this information and understand how images are formed according to diffraction, and now resolution depends on wavelength and the numerical aperture of the lens. And there is a fantastic set of experiments that were done by ABBE and that are here demonstrated by Peter Evanet. There was this senior microscopy from the Royal Microscopy Society. And we have 10 minutes movie. He will explain this beautifully, and then we will comment on this. Let's play.
Now we'll move on to the experiments themselves, which center about the diffraction slide. So I'll pick this up and put it onto the microscope. And there on the screen, we see the pattern that is on the slide. We have a fine grating at the top of the screen with a spacing of 8 micrometers and a coarser grating at the bottom with a spacing of 16 micrometers. I can bring in the diffraction pattern at the top of the screen. In the first focal plane of the condenser, we...
So what is how does it show the diffraction pattern? So he has a microscope with 2 cameras. So one here and one here. One camera observed the specimen, which is this one, and the other camera observed the back focal plane of the lens, where you can observe the diffraction pattern, and usually, actually, we don't see it because we do have the front focal plane where the object is, okay? So, but he is giving us this 2 view, so we see the light and the diffraction of the light caused by the specimen. Okay, let's continue.
We have a pinhole. I can move that pinhole a little bit to the left and to the right, and you can see the image of it up at the top of the screen. You see also that if we just move to one of these gratings, say the fine one, we get a very nice diffraction pattern at the top of the screen. Repeat images of this pinhole here. We can be calling this the 0 order beam, the 1st order beam, and the 2nd order diffracted beam of this particular specimen. Notice that the longer wavelength, red, is diffracted through a greater distance, a greater angle than the shorter green and even shorter blue wavelengths. If I bring back the coarse grating like that, you'll see that the spacing of the diffracted spots is now closer together. So you see that there's an inverse relationship between the spacings in the object and the spacings in the diffraction pattern. Wide-spaced object, close-spaced spots in the diffraction pattern. Have a look at the effect of changing objective aperture on resolution, and I shall do that with the little iris diaphragm, which I can put into the back focal plane. So I shall put that into the slot in the objective like that, and to show you.
So closing and so placing this diaphragm it will virtually decrease the numerical aperture of the lens, because it will create a smaller and smaller opening, so less and less light will go through. Okay,
I can take away the pinhole and look at the back focal plane of the objective, and there you can see that the iris diaphragm there is lying in that same plane. I'll put the pinhole back there and check for concentricity. Just a tiny adjustment there. And then we can bring in the final image plane like that. Now we're ready to look at the effect of changing objective aperture. What I'm going to do is close down the diaphragm in the back focal plane so that first it removes the diffracted beams from the fine grating, and then as I proceed further it will remove the diffracted beams from the coarse grating, simply leaving the 0 order. So let us now have a look at the effect of that. I shall find both gratings here like this and close down the objective aperture, and notice that we've lost resolution in the fine gratings first, and now we've lost resolution in the coarse as well. As I open up the aperture of the objective, first the coarse gratings resolution comes back, and you'll see that that on the top of the screen has coincided with the return of the diffracted beams, the first order diffracted beams from the coarse grating, and then the fine grating comes back. And again, you can see that that coincides with the return of its diffracted beams. To make that clearer, if I move it so that we only have the fine grating in the field there, so we have the diffracted, it's just the first order diffracted beams of the fine grating, you can see here very clearly that if we remove the diffracted beams, leaving simply the zero order, we see no fine detail in the image. I often do a silly experiment here. I simply take the slide off the stage where we have a zero order and no information in the bottom of the screen in the final image. Put the slide back, the diffracted beams reappear and the lines in the image reappear. So there you see the effect of varying the objective aperture on resolution. And the larger the aperture, the finer the detail can be seen. We'll now have a look at the effect of wavelength of the illumination on resolution. Here I've got a filter carrying two colors, green and red, and I can put that in the light path here, green and then red, and maybe turn the light up a little bit. You notice that it's in the plane of the illuminated field diaphragm, so it's possible to see both colors illuminating simultaneously, green in one part of the field, red in the other. What I shall do is close down the diaphragm in the objective lens, reducing the aperture, so that virtually no red diffracted light can enter the system. Touch that up a little there. So now you see that we're not resolving in the fine grating. I shall move that to the green part of the filter, and immediately you'll see we do resolve. And the reason why is obvious, that some green diffracted light of the first order is squeezing through that carefully adjusted opening, whereas that opening is not sufficiently large to accommodate the more widely diffracted red light. So there you see the grating not resolved in red, resolved in green, and if I go to the junction between the two colors in the filter, you'll see simultaneously that we have resolution in the green, but not in the red. So earlier we saw the influence of objective aperture on resolving power. Here we see the influence of wavelength on resolving power. And in fact, they're both parts of the same thing. They're both to do with whether we can get diffracted beams through the aperture of the objective, either because of the size of the aperture of the objective, or for a given size, the angle through which the light has been diffracted when it arrives at the back focal plane of the objective. We'll now return to the more normal situation. I'll take the color filter out.
So this is super important. I think we have one last minute, but certainly of the movie. But you could see all the considerations we have done. So diffraction is like so the diffraction pattern is function of the size of the object, and smaller the object, larger the diffraction pattern. Okay. And then it's inversely proportional to the wavelength, because shorter the wavelength is smaller, so it's actually directly proportional. So the smaller the wavelength, smaller the diffraction pattern, and then that's why to squeeze the information in numerical aperture is either you have like a large numerical aperture for tiny object that have like a giant diffraction patterns, or you have like very short wavelength that they bend less and they can fit inside of the opening of your objective. And now he will explain this in the last minute, basically.
Open up the diaphragm in the objective and put, for the moment, both gratings in position. Here we have quite an array of diffracted beams. Probably you'll be able to see even more if I remove the diaphragm. We've got the zero order, we've got the first order of the course, we've got the first order of the fine and the second order of the course, we've got the third order of the course, we've got the fourth order of the course and the second order of the fine, and so on. Do we need all those beams in order to resolve? Let's explore. I shall put the diaphragm back in like that, and let's do the exploration simply with the fine grating for simplicity. And I'm going to close down the diaphragm a little bit. In putting it in, I've already partly removed the second order of the fine grating. But if I close it down just that little bit more, now we are building an image and a resolved image too, with the 0 and 2 first order beams from this fine grating. Do we need them both? We clearly need some of them, because if we just allow the 0 order in, we're not resolving. But if I slide the diaphragm sideways like that, you can see that if we simply include one diffracted beam and the 0 order beam, we are resolving. So we didn't need them both. Do we need those two beams? Clearly we need the diffracted beam, because that we've already seen is the information. But if we simply include the one beam, the diffracted beam, first order beam there, we're not resolving. Wonder what about the second order beam? Now here we have the first and second order beams of the fine grating and no 0 order, and we are resolving. Yes, the image looks a bit different, and we'll come back to the reason for that difference in a minute, but we are perfectly well able to resolve those lines. So it looks as if we need two beams. In this case, we've got the first and the second orders on one side, or we can have the 0 and the first order. We need at least two beams, because, as we'll see later on, the final image is due to the interference between two diffracted beams, be it the 0 order and the first, or the first and the second order, or the whole array of beams, depending on the situation.
This is the milestone. So the image formation, this is what ABBE did, and what Peter Evan repeated in a really incredible manner. So it's really so we can finish with this work. So he quite a performer, and he was teaching for many years. But then it's clear that basically now the image is due to interference, because like ABBE with his experiments demonstrated that to build up the image, the result image, you need at least two rays of light that could interfere together. You cannot do it with one. And if you have just one ray of light, you would have no interference, right? So you need to have at least two waves, two rays to have interference. And that's clear if you think. So when you have interference, you have like a portion of light that is so the image. So you have like the interference factor that is like dark and brightness. So darkness and brightness. And to observe the feature of your specimen, you need darkness and brightness. If you have only brightness and there is no interference, you see all white and there is no information there. When with interference, you instead build up the actual information. And then the problem is that if you remember then here, tinier the structure that we observe, larger the diffraction, the diffracted pattern and pattern. Okay. And then like this. While when we have large structures and coarse feature, we have a diffracted pattern that is like this. Okay, with the zero order, first order, second order of diffraction, third, and this is the zero order, the zero, the first, and the second. Okay, so then it's much easier to collect the information and the diffracted beams for coarse features because the diffracted pattern is smaller, okay, and will fit inside of the numerical aperture of in the angular aperture of your objective. But with the same angular aperture, there will be a limit. So you see, if we have the same, in which we will collect the zero order that is generated by the very tiny features, but we will not manage to get in even the first order of diffraction generated by those tiny features, because it's tinier the feature, farther and farther away will be the very first order of diffraction. Okay, and then he showed you that this depends also on wavelength, because then when you have the same numerical aperture and you cannot resolve in red, green still squeeze in because diffracts less. And then so resolution depends on the numerical aperture and the wavelength of observation, which is exactly what ABBE then described mathematically, right? Okay, so this was for the first time, all the set of experiments they showed beyond any reasonable doubt that the image formation was due to interference, and that resolution was directly dependent on the wavelength. The minimum resolvable distance was directly dependent on the wavelength, and inversely dependent on this angular aperture of the lens. All right, so let's come back. I will share my screen.
Can I ask a question, sir?
Yes.
Can you just, maybe this is stupid, cheat on achieving resolving power using a monochromatic light source that emits only longer wavelengths?
So you're saying let's use monochromatic light, and then we use longer wavelengths, and in this way we might resolve differently. So this is what we do when we do fluorescence. So we observe one wavelength or like a really short window, small window of wavelength per time, and we have our fluorophores in green, in red, in blue, and so on. But then remember, longer wavelength is larger minimum resolvable distance, because there is like the diffraction is actually larger, and then shorter wavelength use so have a smaller diffraction pattern, and you will have higher resolving power. So you can use it, you can do it with a monochromatic wave, but you need to use both wavelengths. And the visible is limited to this like 400 nanometers. You cannot go much shorter than that. Okay, so we already did all this consideration. We don't need this minute break. Let's talk instead about aberrations and their corrections, and then we come back to the question that you asked me about, like the so using the oil that is thicker than the glass as a higher reflective index. Okay, so so simple lenses, they do not have so they do not act as perfect lenses, and they suffer from several aberrations. So the main three aberrations that we have are the spherical aberration, the chromatic aberration, and the field curvature aberration. Okay, so they are all caused by refraction and or the curvature of the lens. So resolution is highly limited by diffraction. Aberrations are highly caused by refraction, okay? And then there is lots of reading. Okay, we can do it. So regarding the spherical aberration, this is due to the fact that the lenses that we use in objectives are cut out of portional spheres. They are curved, they are thicker in the middle and thinner in the borders. So even monochromatic light travels through different portions of the glass. It has different length of the light path, and it will go through different angles because the surface is curved. Okay, so and this will create what is called spherical aberration. I'll give you a demonstration in a minute. And due to the fact that light is slowed down in a wavelength dependent manner, do you remember that I told you that if you shine white light through a prism, then you have all the rainbow colors because the refraction happens in a wavelength dependent manner, and in the shorter wavelengths they are refracted more than longer wavelengths. Okay, because of this, then you have chromatic aberrations. So if you observe different wavelengths, they will be actually banded differently, and they will have different focusing points. We will see also this in a minute. And then finally, because lenses are cut out of portional spheres, they have a curved surface, so they will normally tend to focus the light on a semicircle or like a semi-spherical surface. And in fact, in the past, at least when I was a student, there were like microscopes where you were putting in focus the center of the field of view, and then the border was like out of focus. Then you were putting the border of the field of view in focus, and the center was out of focus because the focus was not on one single plane, but on a semisphere or a semi-spherical plane. All right, so spherical aberration. So this is what happens. So when you shine light parallel to this, like a converging of positive lens, where you have actually peripheral rays of lights that are focused closer than central rays of light. So generating actually a defocusing of the object that is creating this, that is sending the information. And here you have what is called the disk of minimum confusion, because it's the part where they are like closest together, but it will not give you anyway good image. And then here we have like several rays of light parallel, and I shall put a converging lens in front of them, and then you might need to get closer to see well. But our green laser identifies the optical axis, and we have peripheral rays and internal rays or central rays of light. And you will see here that peripheral rays are focused before the central rays, as I show you in the scheme before. Do you manage to see also from the distance? If you want, you can quickly come close and have a look there. And there are corrections for this, and I can show you that if we put like a lens that actually diverges the light in an appropriate manner, and it's opposite to the converging lens, then we can focus all the rays in the correct position. And that's why objective lenses that are corrected, they are made of multiple lenses, because each lens compensates for some aberration. All right, so this one is a very simple demonstration. These are very simple lenses. But it gives you the first point, and this also brings me to the fact that we have, we need to share again. Okay, so we have spherical aberration also due to the thickness of the cover slip, which is enormously important when you hunt for resolution, or even when you go for super resolution, you hunt for the tens of nanometers in light microscopy. So this is our usual setup. You should recognize it. It's our slide, our mountain, and the cover glass. And glass has a refractive index of 1.15, and air is 1. Optical axis, and this is our specimen. We are not considered, for simplicity, that fact, and so we are considering that the specimen is as close to the cover slip as possible, so the light goes directly to the glass. Okay. So then you already know that it will diverge the light. So, and that the critical angle when the light passes from glass to air is inside of the glass 39 degrees and 72 degrees outside of the glass. Okay. Beyond this, we will have actually the real critical angle and the total internal reflection. So light will travel parallel to the glass and it will come back. So beyond this 39 degrees, there will not be information that will leave the cover slip. Okay, this is clear. Then we remove this just to have a cleaner skin there. And then if I click here, and if you have sharp enough eyes, you will see here dotted lines that actually prolong these rays of light, and this represent the apparent direction of propagation of our light. Okay, so what does it mean? That if we look through our microscope, so this ray of light will appear coming from this position, and the same for this, while this ray of light will appear coming from this position, while, for example, the central ray of light will appear coming from really the specimen itself, because it will not be deviated, because it goes perpendicular. So this will actually create, as we were saying before in this example, an elongation of the structure observed in the Z optical axis. Okay, so there is a dispersion, defocusing in Z of the structure we are observing. And then if we have a much larger cover slip, this is very exaggerated, guys, but it's only like to serve the purpose. But let's say any kind of different size of cover slip will, so light will still travel, as you learn, from glass to air with the same angles. But then if you look now, the apparent direction of propagation of these two rays of light that have the very same angles of these two, but they are much farther apart and in completely different positions. So creating a much larger defocusing of the structure that will appear enormously more elongated, all right? And it will also have really negative effects on your contrast and the amount of signal that you will collect. Why? Because the photons emitted by the specimen are always the same, but you are diluting these photons on a much larger volume, all right? Okay. So more blur, less contrast, lower resolution, and higher level of distortion. And then, what if we have oil, as your colleague asked, that is actually with a higher refractive index of glass? So then the rays of light will be converging instead of diverging from the optical axis, because they will slow down. Okay, you will collect more rays of light, but the problem is that then your structure, instead of appearing so elongated, will appear squeezed. And in lots of super resolution techniques, okay, so you see cells or structures that appear in Z completely flat, because there is some error in sample preparation, and one of the very most common errors is that the specimen is not as close as possible to the cover slip, but there is like some mounting medium, for example, mobile, which is glycerol based. The glycerol has 1.45, 1.42 of a refractive index, and glass is 1.5. So it's the same situation of having glass and a thicker oil on top. So then, if you have like 10 microns of this glycerol between your specimen and the glass, light will first pass through glycerol, then bend inwards into the glass. You are using an oil lens, so the oil will not change anything. So it will go to the glass, to the objective, and then because of this bending inward of the light, you have like structures that are artifactively squeezed, squashed. And Pedro might tell you like a lot about these things. He is an expert on super resolution sample preparation. Okay, so this is the problem if you use very thick. So it's extremely important to match the refractive indexes of your sample and of your cover slip. And then if you have, of course, a huge sample, a very thick one, like a brain slice, then the refractive index of your sample is more important, so play an heavier role of the cover slip. If you are imaging something very thin at the cover slip, so for example, a monolayer of cells, then matching the refractive index of glass plays a much more important role than matching the refractive index of the watery medium, for example, of your cells, because you are imaging at the glass. All right. So I hope that these considerations will be important for you. And one thing that I didn't write here, so always use cover slip that are 0.17 millimeters thick, plus minus 0.005 millimeters. Or you can also find them as 170 microns, under 70 plus minus 5 micrometers. These are the cover slips that are not just the number 1.5, but they are number 1.5 highly selected. So they really need to say this or this, because if you just buy the 1.5, they will have a range that goes from 0.16 to 0.19 millimeters. And then you understand that when you have like 100 microns difference in your thickness of cover slip, the quality of your images will change enormously. It doesn't matter if you do super resolution, but if you do super resolution, it's even worse. But it's and all the objectives, then we will see in a minute, they are corrected for this exactly 0.17 millimeters thickness. So which is this level of spherical aberration. If you get the brown cover slip, you might have a 10,000 euros objective highly corrected that it will not give you good images just because you got the brown cover slip. Okay. And this is just a practical example of what spherical aberration can look like. This is really exaggerated through a single magnifying lens. The chromatic aberration, you already should know it very well. When we shine white light on the lens, even on a single point of the lens, then we will have dispersion. And then since the refractive index actually changes in a wavelength-dependent manner, we will have the short wavelengths that are refracted more than the longer wavelengths, effectively creating different focal points for the different wavelengths. This is very important also when planning your experiments, because then you need to know that your blue fluorophores will be focused closer to the lens, then your green, then your orange, and the red fluorophores will be focused farther away. So if you have, for example, subcellular structures labeled with multiple fluorophores, or you want to observe, for example, interaction between molecules and proteins, whatever it is, you might see the very same structure that were like fluorophores colocalized, effectively colocalized, but in your images they do not, just because of this dispersion or chromatic aberration effect. Okay, and then you see your green fluorophore here and your red fluorophore there. You say they are not colocalizing when they are actually doing it, and vice versa. And you might think, okay, but it's a Z problem. It's also in X, because if we consider only the green focus and the focal plane identified by the green wavelength here, so the image in X and Y will appear like this. We will have our structure in focus green in the center. Then we have an orange disk that is due to the defocus light that comes from the orange wavelength. And then eventually a magenta disk due to the overlapping of the red and blue. And if you put red and blue light together, the resultant is magenta. And so this will be your, so you will have a green focus structure with this halo of defocus light around. So, so your images will be really poor, and your localization on different wavelengths will be really terrible. And the field curvature is that, as I told you, is the tendency of focusing light on a curved plane and not on a curved surface and on a plane. And basically, as I told you, it basically results in this: when you have edges in focus, then the central part is out of focus. When you focus on the center of the field of view, the edges are out of focus. And so objectives are corrected for these three main aberrations, okay? But you need to be careful, because not all the objectives are equal, okay? So we need to learn this. And there are different typologies of objectives. And okay, so the first level of correction is called achromatic. So achromatic lenses. These are the least corrected lenses, but at the same time are the most diffused in every laboratory in the world, because they are cheap, and for relatively quick observations, they might do a good job. They are corrected, chromatically corrected for two wavelengths, the blue and the red, and they are, which is 560 nanometers, 550 nanometers, sorry, 490 nanometers and 660 nanometers, and they are spherically corrected for green, and only for green, approximately 550 nanometers. If you want to know the precise one, it's 546 nanometers. And they can or cannot be corrected for field curvature. So it will be written on the lens, okay? And they might do a good job if you have like a green filter, and then you just filter green light, and then you can see. They are very used in the small microscopes in cell culture. So, okay. The entry level for high-end microscopy are neofluor. We are one. Is it okay for you if we continue a little bit, and then we eat a little bit of your lunch break time? Then otherwise we don't finish this very important concept. Okay, so fluor lenses, they contain fluorite, and they are made with a greater numerical aperture. So the chromatic aberration correction, again, for two lenses is not so much greater, but they are spherically, the spherical aberration correction is also for two wavelengths, and they might or might not be corrected for field curvature. And then we have the apochromat. They possess the highest numerical aperture and the highest level of correction, and they are corrected for three wavelengths: blue, green, and red. For both spherical and chromatic aberration, and they are always corrected for field curvature aberration. Okay, one last thing. So many of the very new generation of neofluor and achromat lenses, they are actually corrected even farther than that. And so this is the default, but the new high-performance fluorite and apochromat objectives are corrected for 4 or even 5 colors for chromatic aberrations, and for 4 in spherical aberration. And this is actually the tab that Zeiss provides, and you will have it so with the slides. But if you want to do colocalization experiments, choose an apochromat lens and not a fluorite or achromat lens. All right, demo of the objective lenses. I want to show you, but then we skip. In reality, we will skip it. But I have many lenses here that have many characteristics, and we can look at them together later. We will not do it now, because I would like to tell you something else. And this is for your own considerations, because there are lots of things that are written in a barrel valence, and you can learn, and it's here in the slides. What I want to tell you is about contrast, because contrast is extremely important also so in image formation, and it limits resolution. So when Peter Evans was saying that resolution is the most important thing, and it's actually limited by diffraction, it is true, but contrast is extremely important too. Do you read anything there? And now, do you read anything? No. And here, okay, resolution is nothing without contrast. So, because these letters are not small. They were there also before in the first line, but you were not able to resolve them and to see them because there was no contrast. So resolution is the most important thing. It's limited by diffraction, but it's also limited by contrast. Okay. So, and then there is a mathematical description of contrast, which is very simple and works very well for microscopy, which is the Michelson contrast, or it's also called visibility contrast, which is basically the ratio between the difference of the maximum intensity and the minimum intensity of the graph divided by the sum of the two intensities, which is very simple to understand. Basically, the contrast goes is comprised between 0 and 1. And when you have a huge difference between your foreground and your background, your contrast is close to 1. And then you have this situation here. When your foreground and your background are very similar in intensities, then your contrast is very poor. And then here there are two, you still see that, but okay, they should be united. And then you will not see the difference between these two squares, which is the same. So black on black, or if you have white shirt on black t-shirt. So this is high contrast versus low contrast. And here, so there is this description is very well done through a modulation transfer function, which is not like something evil. It's very simple. So it's a function that describes the amplitude of contrast in function of the spatial frequency, because contrast depends on spatial frequency. So if we have a structure here that becomes finer and finer and finer and finer and finer, so ideally we will have like a really maximum contrast every time, so in every single moment, independently on the spacing and the size of these structures. But unfortunately, if you remember, in an imaging system, we have diffraction. So when the structure becomes smaller and smaller and smaller, so then we don't distinguish them anymore, because we actually don't see the image of a point is not a point, but it's a diffraction pattern with a disk. So then we have a certain blur that becomes more and more and more, and then we lose contrast, and our contrast becomes less and less and less and less until basically reach 0, and we don't distinguish anything here. And this is also described in this one here, so where we can see with our eyes very well these large structures, but if you go and look toward the center, we don't have the perception anymore. We cannot resolve anymore the tips of these black arrows, and then the contrast decrease here with the decreasing in size of the details until we reach the limit of resolution. So there are many factors that influence contrast. Many of these you already know. We discussed them, like the diffraction and refraction, all the possible aberrations. But there is also reflection, absorption, scattering, phase change, polarization, and more that you maybe one day you will know, you will learn. And we have one method of contrast that we use very much, which is fluorescence. And this is like the key method for all our experiments nowadays. Very few people use other techniques, contrast enhancing techniques. And the definition of fluorescence, we'll read it together. Fluorescence is the emission of light by a substance that has absorbed light or other electromagnetic radiation. In most cases, the emitted light has a longer wavelength and therefore lower energy than the observed radiation. And there are a few things that we need to clarify here. The electromagnetic radiation you already know, wavelength you already know, and the energy. So you know the light is part of the spectrum, and that there is the wavelengths. And but what you don't know is that Planck was put in relationship the energy of light with its frequency μ. So this is the constant of Planck. So the energy of light is equal to the constant of Planck. Wavelengths, less energy, shorter wavelengths, more energy. So now you know that blue light that is shorter wavelength is more energetic than green, which is more energetic than yellow, which is more energetic than red. Okay, and red is the least energetic light. And let's go on because we don't have lots of time, and then I cannot tell you the historical things. But Jablonski was the first one who described in a Nature paper, okay, here. So the process of excitation of these few substances that in the world exist that have these fluorescent capabilities. So of absorbing some light of a wavelength and then emitting light of another wavelength. And then you might know this Jablonski diagram, where there are the electrons of the utmost energetic level of an atom or a molecule, that when hit with an appropriate amount of energy and with a certain wavelength, which means with a certain wavelength, because we know that to a certain wavelength corresponds to a certain amount of energy. So they jump to a higher energetic level, which is called excitation level. And then they spend there few, so a fraction of a second, so few nanoseconds, it depends on the substance and the situation. And they lose some energy in vibrational energy and in heat, and then they come back to the ground state, so their normal energetic state, emitting the residual energy that they have under the form of light. Since they lost some energy, the emitted light is less energetic than the light that they absorb. So it has a longer wavelength, okay? And I wanted to show you this demo very quickly. So this is water, and this is okay. So this is a 405 laser, so which is at the edge of our visibility capabilities. So it's a UV laser, and when we shine it, I will put a screen here to avoid that people get blind so that some accident happen. Okay. So this will collect the light. So this is good water. And if I shine the laser here, we don't see anything because the laser is invisible. So far, so good. Perfect. Now, I will use a substance that is actually tonic water, and it has fluorescent properties, and it's excitable with a near UV light, so 405 light. Okay. So, and I will show you the difference between water and this substance that looks like water. Okay, and here, do you see the light? Now, what you are seeing there is not the laser, because the laser is invisible. In fact, we don't see anything there. So we see that we are heating this substance with invisible light, and then we are seeing visible light. So the substance is changing the nature of light, because we have not visible light and then suddenly we see light, because the substance is absorbing energy and giving back energy, but at lower level that actually falls in our visible spectrum. Okay. Okay. And then what I want to show you is that here I have an array of fluorescent liquids that are all excitable with longer wavelengths. So progressively less and less energy. Do you read like these cards? So the first one was 405. Okay, doesn't matter. This is the 488. It's very important. Okay. Okay, and we have water there. And if I use the 405 light, so what happens is that we see the excitation of all the liquids until the very end. Do you see that there is light even the 600 nanometers excitable fluorophore? I can do it from the other side for just to show you better. Do you see that I can excite all of them? Okay. That's because this is a very short wavelength, which means lots of energy. And this flow force requires packets of energy that are, apart this that requires exactly 405, all these others, they require lower level of energies. But exciting an electron or like a fluorophore, and the electrons of a fluorophore is like buying anything in a shop. If you go with the right amount of money, you will get what you want in the shop. If you go with less money, you will not get what you want from the shop. But if you go with more money, you will get what you want from the shop. The difference is that then you will not get the rest from the fluorophore, okay? Since this is highly energetic, so it's near UV light, so all the fluorophores that require less energy will actually be excited and be happy to take the energy and then produce the fluorescence. But what will happen if I now use a 450 nanometers laser? This is visible, it's blue, it's 450. What do you expect? Say.
It starts at the finish looking liquids.
This one?
Yes.
I think it will also do this because this is 456 as a requirement. This is 450, so it should be fine. Let's have a look. Ta-da! So this one doesn't. So do you remember the difference? Okay, and you see a little bit of light there, and you might say, "Oh, there is I see something." It's anyway like. It's not, it's just that this is not invisible. So that what you see there is the laser. That one is instead the fluorescent effect, so the emitted light. Okay, and if I use a green wavelength, so which is 532 nanometers, what would you expect? I need to put this. So this is like approximately 520, and this is approximately 560.
Just to mention it, the two last ones.
Two last one, or maybe even the third. Let's see if we get it. The third works already.
Yeah.
Okay. So because it's 530, so it's very close. Okay. So you see, but all the others cannot be excited because we are delivering a certain quantum of energy to this, and it doesn't matter how much time we actually stay there exciting, they will not absorb a continuum of energy until they are satisfied. We are delivering a discrete packet of energy. There are four quanta, and then if you have that energy, then they will emit they will go through the Jablonski process, and then they will absorb energy and emit the energy. Otherwise, they will not, and they will never do it. So, and the last one of all of them is the red light. Is it this one? And here, 636. And what will happen?
630.
Is 630 this one?
No one is.
So there should be on the last one because it's approximately 600. Okay, so that one. Okay, and then you have we cannot excite all the previously, so all the previous one. Even if I do on the other side, you see, so it doesn't matter. So the others they don't react at all. So 0. And so this is also actually a demonstration of the particle nature of light, but this is another story. I'm telling you. This has fundamental implications in your experimental plan, because when you observe DAPI, GFP, cherry, and then your parallel fluorophores, if you start with DAPI, which is excited with 4 or 5 near UV laser, you are already bleaching all the other wavelengths. And then you do the green color, and then you are bleaching the red and the far red. Then you do the red, and by the time that you do the far red, you already bleach it 4 times, okay? And this happens like plane by plane. So do it in the other way around. Start imaging the longest wavelength, because you cannot excite the shortest wavelength. You are not bleaching the other fluorophores, and then go progressively to the shorter. The shorter will bleach the other, but you already imaged, so then you don't care anymore. Okay, and then, yes.
Laser will the photo bleaching effect be greater?
The photo bleaching will be greater, it's true. That's why for life cell imaging, so it's not really advisable to use very short wavelengths. So, yes, there is cells will suffer. Okay, I need to share this, and then the last considerations, and then it's done. Then, so, why is fluorescence important? Then you know, so most biological samples are transparent, and then we need contrast, and Czernik invented like the phase contrast in 1937, but we need more because you don't have discrete, with phase contrast, discrete separation, or like you cannot distinguish among the structures inside of a cell, or like you cannot label differently different structures in a tissue or different population of cells. So why there are these fluorescent molecules? Okay, so in 2008, Shimomura, Shalfi, and Sien were awarded with a Nobel Prize in chemistry because of the discovery of GFP. And then, so, which is like this green fluorescent protein that was isolated first from the jellyfish Aquarium Victoria. And then they actually developed all these arrays of fluorophores. And then with this array of fluorophores, we could not only have like really strong contrast, because we have like a black background with really with nice and with strong colors, but we can also selectively label different structures, nuclei, and then microtubules, actin filaments, and these are just examples. In fixed samples like this or like this, this is a brain fly brain. Or in living specimen, this is like embryo development of zebrafish, image towards 18 hours. These are neurons, and this is the head of the fish, dorsal view. This is ventral view. You can see the brain growing and all the neurons going around, and so you can observe both living and fixed samples. And with this, I will thank you all. I'm happy to take questions, and I managed to do it with only 20 minutes of delay. Thank you very much, guys. I hope you like it, and please feel free to ask questions.
Does the shape of the sample also affect your...
It does. It does. So if the sample is very thin, then you can approximate distortions to only the cover glass and the air or the medium of observation of the lens. Okay, but if the sample is thick, like a brain slices or the Drosophila brain that I showed you, there is like approximately under 20 microns. But anything that is larger actually than 10 microns, so thicker than 10 microns, if you want to do high resolution, and so it will actually affect your level of resolution contrast and dispersions and all your aberrations. So in fact, for example, I have a practical example to bring you. So I observe, so there is a group that is studying in a mice brain, so formation of like dendritic spines upon behavioral task learning. Okay, so the hypothesis is the mice learn a task, and then in that specific area of the brain, then there are dendritic spines that are actually increased in numbers and volumes with respect to mice that have never learned that specific task. Okay, to see this, we have to hunt the nanometer and observe these dendritic spines that are in the order of the 100 nanometers, sometimes even smaller, in brain slices. And there is a huge difference in neurons that are close to the cover slip and neurons that are 30 microns deeper in the same brain slice, which is in total 50 microns thick. So we lose completely with an oil lens all the details when imaging deep, because the oil lens measures the refractive index of glass and gives you an advantage at the cover slip, really close there. But once we go deeper into the brain, actually a lens that is made to image through glycerol, which has the same refractive index of the tissue, it gives an advantage, although it has a slightly lower resolving power. So it depends on the thickness and it depends on the level of resolution that you want. If you want to go for super resolution, 10 microns might be even too much. Anything else? Okay. So then, guys, I'm really happy that I taught you all these concepts and that you followed. Let's go for lunch. And in case you need you have any burning question, you can send an email, ask the contact to Pedro. So I will be happy to answer. Okay. Thank you.
Thank you.
Thank you.